The last type of electrophile that react with enolates are the alpha-beta unsaturated carbonyls. An alpha-beta unsaturated carbonyl has a double bond in conjugation with a carbonyl. And this gives it special reactivity since it's electrophilic at two different positions, the carbonyl position and the beta position. So attack at the carbonyl is called 1,2 addition, while attack at the beta position is called a 1,4 addition. So why does 1,4 addition even occur? Well, in the LUMO, the largest coefficient lies on the beta carbon. And we can see this from the resonance forms. And so if we take this structure here and we undergo resonance, we can take these electrons, move them up. This gives us an indication of where the 1,2 reactivity is. But we can, of course, resonate once more, and that gives us a system that looks like this, in which now we have a positive charge on that beta position. And so in the LUMO, right, the greatest coefficient lies on the beta carbon. And this is important for reactivity, because under thermodynamic control, the 1,4 addition product, or sometimes known as the conjugate addition product, is favored. So this is under thermodynamic control. So these again are high temperatures and long reaction times. However, under kinetic control, you're going to favor the 1,2 addition, and this is because this is driven by electrostatic interactions. Right? The carbonyl carbon has more delta positive charge because of its proximity to the electron withdrawing oxygen atom. In the case of 1,4 addition, the conjugate addition, this is under thermodynamic control because there's maximal orbital overlap because that LUMO has the greatest coefficient on the beta carbon. Now this all matters because enolates are soft nucleophiles and will attack in a 1,4 fashion. Right? Other reagents, things like Grignard reagents or LAH or organolithiums, are hard nucleophiles, and they'll attack in a 1,2 fashion. And so let's take a look at some of those reagents. So if we take, for example, methyl lithium in THF at minus 78 degrees, we know that the methyl lithium is a hard nucleophile. And so it's going to react at the hard center. It's going to react at that in a 1,2 fashion. All right, and so we're going to get nucleophilic addition there to give us this tetrahedral intermediate, which then undergoes proton workup to give us the tertiary alcohol. And this tertiary alcohol, of course, still has that double bond intact. And so we say this is a 1,2 addition product. Softer nucleophiles, though, will react in a 1,4 addition manner. Okay, and so, for example, if we had phenyl sulfide, or phenylthiol, excuse me, in DCM, this is a soft nucleophile. And so it's going to react at the position that has the greatest coefficient in the LUMO, and that's going to be the beta position. So it attacks that beta position, and then it's going to move the electrons appropriately. And so now we have a new carbon-sulfur bond here. And then we get loss of a proton to give us this species, which then undergoes reprotonation to give us the now conjugate addition product, or 1,4 addition product, where we've added that nucleophile to the beta position. Now there's one more type of nucleophile that can react at the 1,4 addition, and it actually derives from Grignard reagents, but it's not actually the Grignard reagent that is adding. So let's say we take this ethyl ester, right? And so this has reactivity both at the 1,2 addition or via the beta position, right? So at the carbonyl carbon or the beta position. And let's say we were to take the following set of reagents. We would to take bromobenzene, and then we're going to react it with magnesium metal, and that's going to generate a Grignard reagent. In Grignard reagents, we said are hard, and so they would react at the carbonyl carbon. And that would be the case if we ran this reaction. But if we instead added a little bit of copper iodide to this reaction, you'll form what's known as a cuprate. And the cuprate is a soft nucleophile. And so the soft nucleophile is, of course, going to add in a 1,4 fashion, and then if you quench with ammonium chloride, you're going to get as if you've added a phenyl nucleophile in a 1,4 fashion to that beta position. So this intermediacy of the cuprate which is a soft nucleophile, gives us the 1,4 addition product. And so I'll just come over here and label some of the other types of nucleophiles that are going to be hard, things like Grignard reagents, LAH, and organolithia. And then for soft nucleophiles, things like cyanide, we have the sulfides, azide, amines, and of course the cuprate that we talked about. Now, enolates, as I said, also are going to react via the beta position. And the reaction that illustrates this is a reaction known as a Michael addition. So we haven't talked about enolates yet, despite this being the enolate chapter. Michael addition is the addition of an enolate to an alpha-beta unsaturated carbonyl with 1,4 selectivity, 1,4 addition. Okay, so let's say we start with this dicarbonyl. And we're going to react this dicarbonyl with this electrophile. And we're going to do this in the presence of sodium ethoxide. And again, remember that the base matches the ester. And what we're going to get is a product that looks like a conjugate addition product. So this product is a 1,5 dicarbonyl. Okay, so if we say that this is position number 1, 2, 3, 4, 5, that's a 1,5 dicarbonyl. And we're really making this bond here between carbons 2 and 3. And so we again have, if we're thinking about this retrosynthetically, an enolate piece and an electrophile piece. Of course, what is that electrophile? That electrophile is the alpha-beta unsaturated carbonyl. Okay, so how does this reaction work? Well, if we react ethoxide with our dicarbonyl, we're going to get a deprotonation. Right? So we're going to get deprotonation to give us an enolate. And this enolate is then going to react via a 1,4 addition pathway because it's a soft nucleophile into the other reagent, that alpha-beta unsaturated carbonyl. And so we're going to get a system that looks like this. A new bond is formed in between the enolate carbon and the beta position. And then finally, in order to get product, we simply just need to protonate, and so the electrons can move down, grab a proton from ethanol, regenerating ethoxide, and then you have your 1,5-dicarbonyl product. And so this reaction is known as a Michael addition, and we can think of it retrosynthetically as a 1,5-dicarbonyl coming from an enolate reacting with an alpha-beta unsaturated carbonyl. Or reaction that involves enolates reacting with alpha-beta unsaturated carbonyls, and that's known as a Robinson annulation. So the Robinson annulation is a 3-step sequence. It's a Michael addition, followed by an Aldol, followed by an E1CB. Okay, so let's say we have this carbonyl, dicarbonyl here, and we react it with this alpha-beta unsaturated ketone. And we're going to use KOH in methanol. So just a base. The product that we're going to get here is an annulated product. And an annulated product means that we're forming a new ring. And so you can see here that we start with one ring, but we're going to end up with 2 rings. These are a ring fusion. And so how does this happen? Well, we need to follow the sequence. We're going to first do a Michael addition. And so, of course, we have an alpha proton right here. That alpha proton is the most acidic alpha proton because it's in between 2 carbonyls, right? And so we can get the OH to deprotonate and give us an enolate. And so we have this enolate here, and this enolate is then going to react with our alpha-beta unsaturated carbonyl. And so we get a system that looks like this. So this is the Michael part. Okay, so we have now a new carbon-carbon bond in between the enolate carbon and the beta carbon. So we formed this new carbon-carbon bond right here in green. Okay. At this point, we need to undergo a protonation event. And so we can take methanol and do a protonation. And that's going to give us our Michael product. Okay, now we need to do an Aldol reaction. So an Aldol reaction involves a deprotonation of an alpha proton to give us an enolate, followed by addition into a ketone or aldehyde. Well, we have ketones here, and so we know that that can be our electrophile. So the question is, which alpha protons are we going to react? And it turns out we're going to react this alpha proton right here. And the reason is because that is what's required for our bonds to form. If we look at the structure here, this species in our product comes from that right there, that substructure. And then the other part, right, comes from this part. Okay. So if we were to do a deprotonation, we would get a species that looks like this. And then that can perform an aldol reaction at this carbonyl, which is the carbonyl we want to react with. And so we can get an aldol reaction to occur. Intramolecularly, it's going to be fairly fast. And so that's going to give us this alkoxide. This alkoxide can, of course, then become protonated. We have methanol around to give us this species. And so we've done the aldol reaction to give us the aldol product, but we need to keep going and do the E1CB. And so I'll just label the aldol reaction here. Okay, so the E1CB is, of course, going to involve another deprotonation to eliminate water across that carbon-carbon single bond. All right, so we first form an enolate again. And then, of course, we can get collapse of that intermediate with loss of water as a leaving group to give us the Robinson annulation product. So the E1CB is this step. And so in a single reaction flask, we can take two seemingly unrelated starter materials and bring them together into forming a new ring. This is called a Robinson annulation. And so when you see rings connected together like this, or any ring to form for that matter, giving you an alpha-beta unsaturated carbonyl, think about retrosynthetically disconnecting it into two pieces, an enolate piece and an alpha-beta unsaturated piece, that follows a three-step sequence: the Michael addition, the aldol reaction, and the E1CB.